All right, our next speaker is Dan Talayco from Barefoot Networks. He's going to tell us about a more flexible way to parse protocol headers and perhaps some other things with P4.
So yeah, I want to talk a little bit about P4. The name comes from a paper, and I don't know if I can get it out at the beginning of a talk, but I'll try. Programming Protocol Independent Packet Processors. The language is derived directly from the name of that paper. This is a bit more esoteric than the talk so far, so I apologize for that up front. And I will, in case Uri comes back, he's back in the room, I will mention OVS at least once. Originally, when I got involved with OpenFlow, I was really happy to be involved with a project that seemed to have merely its goal of being involved in the restructuring of a $20 billion ecosystem, and I thought that was pretty impressive to begin with. I've come to think that we're actually looking at something a little bit more fundamental than that, even in some respects. I think we're, this analogy of Linux reshaping how network operating systems were conceived and deployed, I think was a really cool analogy, and it's clearly part of what we're doing. But in some ways, I think we're actually looking more fundamentally at the abstraction of what is the proper CPU for network computation, for network processing. And that was why that's kind of evolved from my experience with P4 in the writing of this paper. So that may be a little bit aggressive for a talk, but the pieces of that I see are parsing, an instruction set architecture, and then control flow. That is, what is the selection of the actions that are going to be applied to a packet as it's being processed as it's going through the network and through a network forwarding element. Today I want to take on one of those pieces and talk a little bit about parsing. We've done a lot of work actually towards this with OpenFlow and with projects like OVS along the way, I think. And I think there's some key points that we can identify that are still holding us up and that we really need to address and change. So to talk about parsing first, I'll just talk a little bit about protocols. They're obviously what make networking work. There are a lot of protocols out there already, and Ethernet. I got kind of bored making the slides, and I needed a little bit of color. There's only 2 color slides on here, and this is one of them. So there's a few more, and as I got involved with playing with PowerPoint, which I don't have the opportunity to do very often, I had to find even the more esoteric animations. Now, all of these are protocols. I think there's nothing esoteric about these protocols. I think every one of them could be explained by someone in this room. Most of us are experienced with at least 80% of them, I would say, and probably to the point where we're so familiar with them that we can tell you what we don't like about them, and the way we wish they worked, and the way we wish this bit had been repurposed, and why the hell do we do this on these protocols? Anyway, so that kind of thing, right? So there's a lot going on here. Not only that, but protocols evolve. Of course, I had to have the obligatory conversation just 10 minutes before the talk about, did you read the RFC I think it was an RFC, for the VXLAN changes that were suggesting that came out last week? I haven't had the opportunity to do that yet. But these protocols are evolving. We're seeing new encapsulations pretty regularly still. Everyone promises to be the last new encapsulation, and it's going to solve everything, and then it doesn't quite work out that way. Even if we did find the ultimate encapsulation, we would really want them to be extensible anyway. You want, option lists of variable length. Each option should itself be variable length. We want new types so that we can extend the types that are recognized within the headers that are available. On top of that, then, networks are becoming more diverse as well. We're seeing things like the growth of MSDCs and other networks with very high performance demands. And the requirements for those are often very different than for, say, a WAN deployment or for an enterprise campus deployment. And the performance has become more and more of an issue on these. It's even become a competitive advantage in many cases as well. As a result, deployments are becoming more and more specialized. And I don't know if you saw the Facebook releases recently, but they're talking, it was a pretty interesting blog post, I think is the way it got published last week. And they're talking about taking BGP down to the TOR. And I think that's great. I think there's, SDN is enabling that, and it's really a big step forward. But, it's the question, is that the way it should be? So in particular, then, I think, we're coming to the conclusion that there's sort of one size fits all, by which I mean that we have a forwarding element. It provides some subset of available protocols, which essentially is going to be a strict subset of those available and, in some hierarchical approach. And that's just not really going to work for us. Well, protocols are defined by field semantics, and parsers identify fields. So it's pretty critical to this whole process. And yet, parsers haven't really gotten very much attention until lately, I guess I would say. Maybe that's because, I was just sort of brainstorming here, and it's because they're too easy. We just sort of see them as a state machine, and we've all drawn the little diagrams with Ethernet, which goes to IP, which goes to this, goes to that. On the other hand, they're very hard. There's a lot of challenges to actually implementing them in hardware, or even software, so they work efficiently at the line rates that we want to support, as those line rates continue to progress by orders of magnitude every few years. At the risk of sounding conspiratorial, maybe they're too important, because if you do control the protocols, you really control the feature set that's available, and you really are able to lock in your customer base in that respect. They're a bit stuck in the past, I would say. We've had static parsing available to us. We're binding the feature changes that we want to make to a much slower development cycle, especially in hardware, but actually in software as well when we do this. If you look at the history of OpenFlow, and the paper sort of starts off with a little introduction about this, in some ways, I think we avoided taking on that challenge. When I was in those discussions in Gates 104 early on, it was kind of like, yeah, the parsing's just kind of taken care of. We don't want to address that. We'll assume it's a black box that sits outside of what we're doing. And however you identify the VLAN tag, we're happy, right? We're not going to worry about how that happens. We've got a VLAN tag. That's all we care about. We're going to match on it. As a result, in part, the field count went from like 12 fields or so in 1.0 through 15 through 36, 40 fields, 41 fields. It's an extensible architecture now, but it's still fairly static in a lot of respects. And so I want to talk about programmable parsers. The idea here is that we should be able to, just like we can push down flows into a table that does match action, maybe not just like that, but at least we should take a step towards that. We should be able to have a configuration or an ability to pass down to the forwarding element what we care about in terms of what are going to be in the packets that we see. Now, obviously, this is possible in software, although interestingly enough, not yet in OVS, and that's one of the calls to action I have in this discussion today. It's also possible in hardware, actually, and there's been a lot of work on that lately. There's one reference there. Glenn Gibb wrote his thesis and published that a year or two ago on exactly these questions of doing this effectively in hardware. So shifting a little bit to the main topic then, if we're going to allow programmability of something like an element of the parser to a piece of the forwarding element, we need some way to represent the programs that we want to be pushed down in there. And that's a part of the P4 language then was focused on that. So let me talk a little bit about P4 in general, and then I'll focus in on the parts that are related to parsing. It's based on an abstract forwarding model that really derives from OpenFlow in a lot of respects. It refines it a little bit, makes it a little bit more specific, and one of the key differences is that it contains a block, which is a programmable parser, and it exposes that. It still has some black boxes in it, and I'll talk about those briefly. It allows the definition of arbitrary headers. So P4 itself is completely protocol independent, completely protocol agnostic. It doesn't throw away protocols. It doesn't say we should have no protocols. It is just agnostic towards the protocols that you actually want to provide in an element, which is programmed by an instance of P4. And once you have that definition of headers and fields and the protocols that you're going to have that you want to recognize, then that provides the context for match action. That's actually very natural in the way that OpenFlow is set up. We just didn't take that step the first time we went to that direction. So here's the high-level P4 abstraction. The parts in color are the parts that are recognized and controlled by P4 for the most part. There's the clear boxes, the white boxes here are black boxes which are acknowledged by the abstract model but are not defined or not, no interfaces are expressed for P4 for the most part. So there's a parser which gets a parse graph pushed down into it during the configuration period. And then based on that, that provides a context for specifying the match action tables. Match action tables look mostly like OpenFlow tables. The primary difference is that you specify the set of actions. You specify essentially what I was referring to before, the instruction set architecture that you really care about applying to tables. You do that at configuration time. And so each table has a set of actions that it can select from at runtime. We can talk a lot about what's runtime, what's configuration time, when can you do this, when you can do that. Right now, P4 is trying to just be fairly conservative, leaves a line between a configuration period before packets are being processed, and after that, when packets are being processed based on the configuration. It doesn't say anything about that you can't reconfigure things, but it's not trying to take on that problem yet at this point. The reconfigurability, that was one of the first three goals for P4, was that reconfigurability in the field was a goal there, an explicit goal. But the reconfigurability means that you don't have to pull out the piece of hardware and replace it with a different piece of hardware. And beyond that, we're looking for opportunities for improvement. So there's ingress match action blocks. P4 does differentiate between ingress and egress match action. This is somewhat of a pragmatic difference. Essentially, the idea is you've got a packet that comes in, you're going to do some processing on it. Eventually, you're going to figure out where it goes. At that point, you probably still want to do some processing on it. And so the difference between the ingress and egress is, at this point, you haven't necessarily figured out where it's going. You're just operating on the ingress instance of the packet. It goes into this queuing or buffering or traffic manager block, and that's what's responsible for actually creating each instance of an egress packet. Each of those instances can be operated on by the egress match action. There are provisions for recirculation and for cloning of packets along the way as well. We don't put those in the forefront because we really want to focus on just getting this part right initially. And then after you have the configuration programmed into the device, then you turn it on and you provide some protocol needs to be provided in order to allow the programming of the tables. Typically, that could be OpenFlow, but we're fairly agnostic towards the particular southbound API, as is usually called. Okay. And, sorry, slides there I didn't know about. Okay, so P4 then is a programming language, and it looks a lot like C in its syntax. In fact, we use a C preprocessor on it in general, and that allows us to automatically gets an include mechanism, automatically allows you to define identifiers that could just use simple macro substitution along the way. That's very convenient. And I just want to give a little taste of the syntax here. The website's p4.org, as you might have guessed, and I'll put that up at the end. That's the place to get the full specification as well as subscribe to to the announce list and so forth, and you can become a member if you're interested as well. So here are just a few snippets of P4 to give a taste of it and explain what I mean when I say programmable parser. And from there, then we can look at what the ways we might go to integrate a feature like that. So headers, as I said, are declared by type, and then instances are declared from those types. Right now, the header types have a list of fields. Each field has its primary attribute as just the width. But you can imagine it's pretty easy to extend this so that fields could have arbitrary attributes. Right now, fields can also be signed, marked as signed, or saturating. And these things aren't really that important for the match action processing until you start worrying about semantics of arithmetic on the fields that you have at hand. And for the most part, we don't have to worry about those. But every once in a while, something's weird, and you want something like, if I decrement my TTL, I don't want it to roll over. Right? And so saturating is the attribute that's used to specify that sort of behavior. But most of the time, we really just care about the widths of the fields. The parser then, the main thing that I wanted to do when specifying the parser is identify these two distinct functions. And if you look at the way parsers are generally specified or drawn or written down, or when we just make references to them quickly, we often sort of confuse these two things that are happening. The intent was to break those out. Those two things are doing what you might call the extraction or the identification or the offset specification for a field. It's saying, where is this field delineated in the packet? Right? That's one thing that a parser does. And then the second thing is, okay, now that I figured that out, how do I move on and look at the next part of the packet? And this is essentially just a state machine, and so that's a state machine transition specification. So it's really in P4 we've identified these two things explicitly. The first is through the extract instance, and the extract it works in conjunction with the header specification. The header gave a layout of the packet on the wire, and the extract just says, hey, that header I just told you about, it's sitting on the packet right now, so go grab it according to that specification. And then, independent of that, we have a mechanism to say, okay, what's the next state? And we have a selection mechanism which allows you to refer to fields within already parsed instances of headers. And in this case, we're making use of the C preprocessor to say, the ether type has these symbolic representations of VLAN or MPLS or IPv4 or V6 or so forth. In P4, this then gives a parsed representation of the packet. And I don't want to delve too much into this. I think it's quite natural. I mean, if you've looked at this from an OVS or from OpenFlow in general point of view, it's a pretty natural idea. You can either view the parsed representation as a block of memory into which I've extracted all the fields from the packet, and then I'm going to work on that. Or you could just view it as a pointer map where I've said this field lives at this offset in my packet data. And if I'm going to make references to that, I'll have to make sure that I've got my endian and field offsets reconciled properly when I actually make those references. As long as my match specifications and my field data are consistent, that should just work out. Although there's definitely a bit of bookkeeping to make sure that all works. The wrong button, that would explain it. So as I said, parsing then gives a context for match in action. So when you specify a table, in this example, I just had an ACL table. You specify the fields that it reads. Those are, header instances and field references within a header. And this is just listing the set of things this thing can match on and the characteristic of the match that it is expecting to do. As I mentioned, this is the list of actions that this table can carry out. Each of these actions in P4 is given by an imperative specification of a function, essentially. And the idea is that function has a bunch of parameters. The values of those parameters are determined at runtime by the entry that's matched, right? So that's how these things all dovetail together. This is really a key piece. I don't have a slide for it, but the runtime interfaces then specify a set of values for the match values, and then select an action, and for that action have to specify the parameters that are made available. Right? Pretty much just very natural from an open flow point of view. So, programmable parsing in OVS. I think it's completely tractable, at least from just a technical point of view, right? We need to have a little bit of indirection there. That indirection isn't going to be very expensive for performance, mostly because I think we can do this at a configuration time. And so it's a matter of just decoupling the way that fields are being specified now through a level of indirection that happens during a configuration operation. And then a lot of the optimizations that are already there can be used to compress field values and do cache matches in the same way that that's being done now. I think OVS is really critical for providing a lot of these deployment-specific features that I was talking about before that are resulting in specialization of network deployments. In particular, for example, this kind of selective protocol engagement, which I wrote down, which I basically just mean a given deployment really only cares about a certain set of protocols, and we should be able to specify that set of protocols arbitrarily and easily. And we want an agile response to the protocol changes that we've been talking about, and I think in overlay and underlay architectures as well, there's a lot of this comes out as well, because you can say that we're just using an overlay architecture, but the particular tunneling technology that you're using may vary from place to place as well, and that affects all of this as well. So, quick slide, plug for the P4 website. The original authors, one of whom is Dan Daly, who was in the room a little bit ago here. You can sign up for the announced mailing list. I promise you won't get very much email on it because there's been, I think, one announcement on it so far. So feel free to sign up for it without worrying about too much spam coming. We're going to try and start sending out some of the key announcements. It'll still be very low bandwidth. So that's it. Questions? What's that? You can't get to the site? I'm sure VMware is blocking it because they knew the talk was going on. Sorry about that. I'll check to see what's going on with that for sure. Since I'm the network admin for it too, I guess I get to do that.
Hi, Chris Wright from Red Hat. Have you had a chance to look at some of the Linux efforts around the eBPF work, and could you compare and contrast P4 with eBPF?
Yes, only recently, let me put it that way. So I don't have a very well thought out response to the question. This is definitely in the same space, definitely very interesting work that's going on there. And there's been a lot of discussion about whether or not P4 could be compiled to eBPF programs as well. And I think there's actually been some people who know more about it than me have actually thought about that and are moving in that direction at this point. Yeah.
All right, thanks. It might help with your call to arms of OVS P4 support. That's why
Okay.
I bring it up.
Great. Great.
Yeah. Dave Tucker, Socket Plane. Could you go back to your high-level P4 overview?
Sure.
Just a clarification question.
Oops, apparently not. This one?
Yeah, that's the one. So just on the point of replication, I think you mentioned that had happened in Traffic Manager or something in the middle.
Right.
So in the case of doing something like an open flow group action to output onto multiple ports, how would that Traffic Manager know to do that replication? Because I didn't see any representation of that from people.
Yes, yeah. So the magic for this block right here is where all replication is the semantics are actually implemented. And there's a notion of intrinsic metadata in P4, which means metadata is just treated like headers in P4, and most of it is scratch space for the programmer. But there are parts that are specific to the operation of the machine and to the specific targets will have their own metadata. P4 has a couple of high-level bits of intrinsic metadata, one of which is called egress specification. And it's a generic bit of metadata which is going to be interpreted by this and is mapped from the instance that's coming in to a set of egress instances that are going out. And so essentially the simplest case is that, you know, we're talking about maybe exposing that as a state machine or even something that could be programmed like a flow table, but a natural mechanism to support that interface would be something like the group tables.
Okay, thanks.
A little bit to tease apart there with the more complex actions that can be specified in group tables and OpenFlow, but the key part of replication is wrapped up there.
We still have time for questions. Any more in the room? All right, well, let's thank our speaker.